spring semester, and spring is really here. In fact, we even think that summer has arrived. Spring was very short. We just had an excellent ITC colloquium by Priya and Natarajan, who will speak to us again at lunch. She showed us some of the latest data from the frontiers fields of HSP. We also, thanks to Priya, have a visitor, Wally Gilbert, that started his career in physics and then went to biology to win a Nobel Prize. Perhaps it's a lesson for some of us. We saw the future, and he came to hear Priya's colloquium today. We will start with our own Aaron Bray, that will talk about galactic conformity in Illustris. And then we'll continue with Priya, that will tell us about the formation of the first black holes at high redshift. And then we'll hear from the CFA colloquium speaker. Is he here? Oh, great. Bob Abraham from the University of Toronto, where the weather is worse than Boston. Not today. And he will talk about biased progenitors bias?
Yes.
Okay. And finally, we'll hear from Cameron McBride that will tell us about post-cosmology, squeezing out more information by considering galaxy properties. Aaron.
All right. Well, thank you very much. The mic is on, it appears. So I'll talk to you today about galactic conformity in Illustris. And my collaborators have principally been Annalisa Pilipich and Laura Salas, who is now at UC Riverside, as well as my advisor, Daniel Eisenstein, and Lars Hernquist. So, quickly, I'll give you an introduction to galactic conformity, why we're using the Illustris simulation and the methods we use to do so, and then I'll quickly get to results. That we find conformity in Illustris, and what we do to verify and try to understand why this is. So, as you know, galaxies grow in dark matter halos, and thus they are linked to the growth of their halos. The question really is in what ways are they linked? What are they linked to? Models of large-scale structure successfully reproduce clustering statistics, but the fundamental ansatz is that halo mass is really the only relevant property for determining the occupation statistics of galaxies and their properties, such, for example, you know that stellar and halo mass are tightly correlated. Recent work has also shown that there potentially are systematics if galaxy properties correlate with their assembly history and not just their mass. So this is something we call halo assembly bias or galaxy assembly bias. Halo assembly bias has already been found in dark matter only simulations. This is the fact that the clustering properties of a dark matter halo are dependent on the assembly history, how the mass forms, how you get to have mass m of a dark matter halo. The question really becomes, for galaxies, are the clustering properties of galaxies dependent on the assembly history of the halo? Or does all the accretion over time erase any knowledge of the assembly history, which is what the ansatz assumes? So, in particular, I'm interested in whether or not the color of a galaxy is dependent on more than just the mass of its dark matter halo. Now, we get to galactic conformity, which was first called this by Weinman et al. In 2006. And this is the idea that the color of galaxies, which I'll call secondary galaxies, at some radius, correlates with the color of a central galaxy at wherever you're looking. So to look at this picture here, the key is that we're talking about fixed primary mass. Now you know that for larger mass halos, red fractions of galaxies are going to be higher. So we're fixing the primary mass. So we have an equal mass red galaxy and an equal mass blue galaxy. And we see here that the red central galaxy in this toy galactic conformity picture, the satellites tend to be red, and around the blue galaxy, they tend to be blue. This is what I refer to as conformity. Specifically, this is the one halo term. This is something we can understand from hydrodynamics. This is something we can understand from stripping, from tidal interactions. It's going to be very complicated, but ultimately, these are things that are very causally obvious of where you might start looking, where they come from. So this is all taking place inside the virial radius. What I'm interested in, and what I probe in my talk today, is the two halo term. This is a conformity between the central galaxy, the color, which is red or blue, and the galaxies that lie well beyond the virial radius. So this paper has spurred a lot of discussion in the field, and this is Kaufman et al. From 2013. And what I'm showing you here is that the log-specific star formation rate of neighboring galaxies on the y-axis is a function of bins and radius on the x-axis. And you'll see here, this red line is the 25 reddest primary galaxies. These are the central isolated galaxies that they've tried to isolate in the SDSS sample. They have neighbors with lower specific star formation rates than the 25% bluest galaxies. This is an observational signature of galactic conformity. So actually, you notice it's true also basically about the median. The 50% most red galaxies tend to have, out to a radius of about 3 megaparsecs, about 0.4 dex lower specific star formation rate than the bluest galaxies. And we'd like to understand why. And so, to get to the punchline, do we see this in Illustris? The answer is yes. Now, I'm plotting it in a slightly different way. We have quench fraction on the y-axis, and we have distance on the x-axis. And this is three-dimensional distance. And I am showing again, these are a population of isolated red galaxies, and these are isolated blue galaxies. And you see that the neighbors in all of these various bins tend to have fewer red neighbors when they're blue, and they have significantly more red neighbors when they're red. And just to guide the eye here, this is in a particular mass bin, but this is approximately the sort of maximum virial radius for something of this mass. So we're only looking at 2 halo conformity here. Sorry about that. And I'd just like to point out that there's both this near field effect, in which it's significantly higher, and then also this sort of plateau that goes out to almost 10 megaparsecs. And it does, and after 10 megaparsecs, I'm not showing you, but it does merge again towards the global mean, which is somewhere in between these two values. So why are we using the Illustris simulation? Well, as you've heard many people tell you before, the Illustris simulation creates a number of realistic galaxies. And more importantly, with its particle resolution and its size, it produces sufficient numbers of galaxies at greater than 2 times 10 to the 9, which is my threshold for looking at these galaxies. So that's about 2,000 star particles per galaxy, sufficient to do clustering statistics. So this is what's really important. We have realistic galaxies, and we have a large cosmological volume. So I apply an isolation criteria very similar to the Kaufman et al. I require that in order to try to select for central and not satellite galaxies of halos, I require that the mass of the central galaxy be at least twice of any other galaxy within 500 kiloparsecs. Likewise, based on the literature and what other people have previously done, I calculate halo ages, because this is something that has been shown to correlate with color and galaxy properties, as well as mass in recent studies. So in order to get these halo ages, what do? I compile the full mass accretion history from the sublink tree created by Vicente that he talked about a couple weeks ago. And then you have to create a smooth mass accretion history from the snapshot files by splining or by creating some polynomial fit. Then the halo age of a dark matter halo is defined as the earliest redshift at which a halo in total mass, stars plus dark matter, equals half 50% of its maximum mass. So this provides an equal definition for satellites and centrals. And they can be treated the same. And then what I call T-form is just a look back time to this redshift where the halo reached half of its maximum mass. Back to the results. Not just the lowest mass bin, but we see this galactic conformity at all different mass bins. So we have different mass bins in stellar mass. Red galaxies tend to be found around red galaxies. And likewise, in approximately equal densities for halo mass, we see almost the same signal qualitatively. What this is telling us is that stellar mass is actually a good proxy observationally for looking for galactic conformity, and we're not somehow being biased by using stellar mass as opposed to halo mass. Because ultimately, what we really want to know is whether or not something other than halo mass correlates with the colors of galaxies. So how do we understand this? Well, there's another signal in Illustris, and that's the dark matter only conformity. So I said I calculated the halo age. And then I divide those up into 2 groups. Instead of red and blue, I have old halos and I have young halos. And what you'll see here is that you have the same signal. Old halos tend to cluster around other old halos, and young halos tend to cluster around young halos. But you also notice that the amplitude is approximately the same across all masses, whereas in the other conformity plots for galaxies, it actually decreases with mass. How to explain this? We also have a color halo age relation. Especially for low mass galaxies, the color of a galaxy correlates very well in the median, this black line, with its look-back time. So older galaxies tend to be redder at fixed stellar mass bins. But this disappears and becomes very scattered at higher masses, which explains why there's actually a decrease in the conformity amplitude at higher masses. This age matching line is showing you the locus of points if you were to match 1-to-1, the bluest galaxy with the youngest galaxy, and the oldest galaxy with the reddest galaxy, and then just go from there. So I've been telling you this story, but how would we test this, at least initially? Well, we use abundance matching first to assign galaxy properties to the dark matter in Illustris. So we're going to take the same halos that we've had that's been created in the volume and basically shuffle what galaxies go where. And we're just going to apply a very simple abundance matching model, putting the most massive with some scatter that's been empirically found to be more or less the case. And then we apply this for both centrals and satellites. Again, our halo mass is the maximum of its accretion history. And we apply this, and what do we get? Well, probably what you thought we would have got. If you get rid of the spatial correlations with the color, you actually don't see any conformity signal. That's because when you do just abundance matching, you have no knowledge of the color of the galaxies here. So do we have to add something? Well, yeah. So we go in and we add this age matching. And we do this where we assign the reddest galaxies to the oldest halos. And we do this in fixed stellar mass bins, the same stellar mass bins I showed you before, of 0.25 dex. And now we do this again. And we get the same thing, the same conformity signal that we found naturally in Illustris, the same one that came out of the large cosmological simulation, just applying a few very basic prescriptions. I'm not saying that this model is right, but that it provides a simple way of understanding what is going on. And likewise, this works at all of the halo mass spins and all of the stellar mass spins. So the story I've told you is that Illustris has a conformity signal that has potentially been found in observations as well and that we're interested in pursuing further. That abundance matching or other models that depend solely on mass are not going to reproduce this conformity signal. And that something like an abundance plus age matching model actually will. So in summary, we find that the color halo age relation exists in Illustris. For low mass galaxies, redder galaxies live in older dark matter halos. We find dark matter only conformity. Older halos, defined by this T formation, which is the 50% formation time of the halos, are preferentially located near other older halos. And then red galaxies preferentially are located near other red galaxies, out to 10 megaparsecs. That's 20 to 40 times larger than the virial mass. This cannot simply be explained by hydrodynamics or close tidal interactions, at least locally. And then we test this with our semi-empirical model, and we find that these two things together, color halo age relation plus dark matter only conformity, is sufficient to qualitatively reproduce the conformity signal. Not exactly in amplitude. We do think there are additional hydrodynamic processes affecting that near term, and that's something I'd be interested in exploring further. But the takeaway message I want you to have is galaxy assembly bias definitely should be taken into account when modeling large-scale structure, as otherwise we may be introducing biases when we try to understand galaxy formation, as well as cosmological parameters. Thank you very much.
One way to think about your results is to imagine that locally some regions in the universe have a higher overdensity on large scales, let's say 10 megaparsec,
Yep.
20 megaparsec. And because of that, the clock is ticking, the cosmic clock is ticking faster in overdense environments like this. So all the galaxies become red because of that. And other regions that are underdense will be blue. Is that the way?
Absolutely. That is currently the way basically that I think about this. And I think there was a recent paper put out on the archive of last week by Andrew Heron and Frank van den Bosch. And ascribes a slightly more physical mechanism for this, having to do with the Hill radius of these galaxies as they track them back in time. And I think it's an open question, really, on to what extent, whether these are saying the same thing or whether you need a physical mechanism, as opposed to simply having a large-scale bias. And in order to start collapsing halos, the oldest halos are going to collapse first. They're going to have little stochastic peaks on the large-scale bias. They're going to be clustered initially. So you just get that dark matter clustering sort of naturally, as other dark matter simulations have found. And then going forward, I didn't show these plots, but the color halo age relation is not something that just appears at late times that you might be concerned. Is this an Illustris artifact having to do with something that we haven't, a prescription, a feedback prescription? And the answer is no. The older halos have very similar star formation histories that just start a little bit earlier. They have slightly different peaks, but if you look at the oldest and the youngest halos and then look at the galaxies in them, they just started forming earlier. And then they stopped forming earlier, and that's basically why they're quenched.
Can you give us any physical feeling for why the red curve, the quenching fraction, levels off rather dramatically at roughly r equals 4 megaparsecs?
Right. So I will note that it's not quite as extreme, and as I said, I think that there's potentially at the first inner few megaparsecs, now these are megaparsecs, not H inverse megaparsecs, I think there could be sort of tidal interactions and near flybys going on that would affect this. But this is a signal that I do think is already there in the dark matter itself. And so this is something where I think trying to pursue the direction, for example, Andrew and Frank are taking, and also trying to understand sort of what the scale of, there's a paper, Dalal 08, that sort of talks about what radius dark matter stripping happens, and at what radius sort of accretion stops onto dark matter halos. Understanding that may give us a sense of why there's this sort of 3 to 4 megaparsec, but I don't know right now. But I imagine that it potentially can be described purely based on the dark matter and not the baryons, is my feeling.
The splashback radius?
For what? For
Dark matter halos, for example.
I don't. So in the Dalal paper, which doesn't include dark energy, but it's just a matter-only universe in which they look at stripping, I don't think it is the splashback radius. It's actually sort of the radius at which larger halos sort of prevent accretion. And this is something that is, along with what Andrew and Frank are looking at, is a similar related issue.
It's worth pointing out that there's no overlays of all the unity on those scales. This is roughly the scale where you get variations of all the unity in the mean density of the unity. So you expect that to be the characteristic sort of building block where one environment is different from another.
May I ask a
Yeah.
question? Is your model degenerate?
With what?
Is your model degenerate?
What's the question?
Is your model degenerate? Do you have enough parameters to actually constrain your model?
Right. So the question, I'll interpret the question to mean as whether or not there are other potential factors other than, for example, T formation and sort of doing age matching, which could provide a similar thing. And I think the answer there is clearly there are other definitions of halo age. For example, Andrew Heron uses a different definition of formation time, and there's a lot of studies that have looked at how formation times, and they give slightly different results. And so that's definitely true. Likewise, I think just, there's a whole parameter space. We have explored some of them. For example, overdensity at 8 megaparsecs correlates not at all with formation time. So sort of certain common things that have been looked at in the literature, like basically overdensity at 8 megaparsecs, does not correlate with this. So simple environment measures or fifth nearest neighbor don't work. So I think that's interesting too.
Thank you very much.
Priya, would you like this?
Better electronic risk. Okay, it's not often that one gets to give a talk along with one's favorite undergraduate, former undergraduate. So Aaron was at Yale. Anyway, so what I want to talk to you about today a little bit is basically give you a snapshot of where we are in terms of our understanding of the formation of the first black holes. There's been a lot of recent progress on many different fronts. So I'll just kind of vignette and show you what the new ideas are because we have only 10 minutes. But one of the biggest open questions with the formation of black holes, the first ones at high redshift, pertain to the fact that there might be a timing problem given observations of bright quasars that we were starting to detect further and further back in the universe. So we now had a recent a report of a quasar that was detected at redshift greater than 7, and the measurement of the black hole estimate of, I shouldn't say measurement, estimate of the black hole mass of 12 billion solar masses at redshift 6 recently reported. So the question is, if the standard idea of having a stellar remnant black hole be the first seed from which we can grow supermassive and ultramassive black holes, do we really have enough time? Can we do all of that? Does the universe give us the right physical conditions to do so in 2 gigayears, for example, right? So that time has been crunching down as we are seeing more and more bright quasars appear at earlier and earlier times. Now, what is interesting is that this is not unrelated. The assembly of the first massive black holes is not unrelated to the conditions that are required for assembling the most massive black holes at every epoch later over cosmic time. And so recently, with the host of multi-wavelength data, we actually know that some of our earlier assumptions about black hole growth have been called into question. So the fact that merger-triggered accretion episodes were fundamental to all black hole growth has now been dispelled, and we now know that merger-triggered accretion episodes are critical only for the most massive black holes and possibly the ones that power the brightest quasars. And that there is likely a long-lived trickly accretion mode over cosmic time that is really relevant for most other AGN in the universe. So, and we also know that the AGN-driven feedback models in galaxy formation, the current ways in which those models are implemented by tapping into some portion of the energy released due to accretion onto the black hole, are actually too aggressive because they actually stunt the growth of the most massive black holes. They quench the star formation all right, but they do stunt the masses of the most massive black holes at later times. So these feedback procedures have been pursued to explain the quenching of star formation roughly at redshifts of 2 or so, and AGNs are now deployed, AGN/actively accreting black holes are deployed for feedback. So it turns out that our current prescriptions are all a little too aggressive. They are too efficient. So they actually stunt the black hole. So we are not able to actually credibly reproduce what we are seeing observationally. Observationally, we are starting to see very, very massive black holes locally. So this is the high mass end of the M sigma relation. So you have these candidates in excess of 10 to the 9, 10 to the 10 solar masses appearing here. And we've also pushed down to start discovering lower mass black holes that are hosted in lower luminosity galaxies, much lower luminosity than the Milky Way. So we've pushed this local correlation. So this is the census of black holes in our backyard. And this correlation, this empirical correlation, has been sort of the foundation for coming up with feedback models, because any black hole that starts off over its mass assembly history at high redshift has to eventually land on this kind of correlation at late times. So we also now understand that the existence of this correlation is really a reflection of hierarchical buildup of structure and merger-driven structure formation in CDM. So just the properties of dark matter halos assembling over time, the halos that eventually host the galaxies that eventually host the black holes, is sufficient to give you such a relation, but the scatter and so on depend on the accretion physics and the initial seed formation mechanisms. So we have data now, not only from our cosmic backyard, but also from very high redshift, these very, very high redshift quasars. Once again, I always like to point out that, finding a couple of freak quasars here and there is not a problem for CDM, because you can always say you have a high sigma fluctuation, a rare peak, and you have this object. The problem is when you start finding populations, and we've started finding populations at redshifts of 6 and redshifts of 6.5 and above. And so one of the other key concepts has been the Eddington limited growth rate of mass onto black holes with a characteristic mass doubling time scale of roughly 10 to the 7 years, the saltpeter time. And this is relevant because it is this time scale compared to the age of the universe at every epoch that really matters. So in what I'm going to tell you today is in all these sort of assumptions that we have made about black hole growth that I said have been called into question, there is one that we are still holding sacrosanct. And I won't tell you what it is, it will emerge. But if we let that one go, there really is no timing problem. Okay, so let me now also show you that one other squeeze on timing comes from recent Planck results that kind of from the estimates of the optical depth are suggestive that you don't actually need to form the first stars. You most likely don't form the bulk of the first population of stars till quite late in the universe. So what that does is that if your first seed black holes are going to be remnants of the first stars, the clock has been pushed back further, making the task of generating 10 to the 9 solar masses of growth within a few 100 million years much trickier. So let me explain a little bit of what the timing challenge is in terms of the seed that you start out with for Eddington limited growth. So this is just a little toy graph that shows you that if I want to end up with a 5 billion solar mass black hole, say at redshift 3, 4, 5, or 6 or 7, so if I want to end up with a 5 billion solar mass black hole at redshift 3, then I could start with a really wimpy seed, a 100 solar mass seed, and I would just need a mean Eddington accretion rate of about 0.4 to make that happen. And of course, this rate, this expected mean rate is lowered and alleviated if I start out with a more massive seed. Now, the problem comes when we have to produce this black hole early and earlier back at higher redshift. For example, at 4, you require a mean rate that is close to 0.55. And of course, if you want to produce a 5 billion solar mass black hole by redshift 7, you can see that you have to exceed the Eddington rate, right? So this has sort of been the kind of the seeding conundrum. So obviously, this is alleviated if you start with a more massive seed, right? And the fact that by redshift 3, the universe is about the lambda CDM universe. I think is about 2.2 gigayears or so. So you have plenty of time. And so for lower mass. For lower redshift, very massive black holes, you have freedom in terms of the seed mass that you start out with. So in order to alleviate this timing issue, we had proposed amongst many others, actually I think Avi and Dan Eisenstein wrote some early papers that were relevant to the formation of sort of direct collapse black holes that could actually be more massive. So these are situations where you have a blob of gas in an atomic cooling halo that somehow bypasses the formation of the first star and directly collapses and gives you a black hole. So the advantage of this is you might be able to, if the conditions are right, and it turns out that you can have the right conditions, physical conditions in the very early universe, you could assemble something that's 10 to the 4 to 10 to the 6 solar masses. Or the traditional route, which is to make the first POP3 star and then start with the remnant of the seed. So there's a timing issue with these guys, and here there's a physics issue of how do you actually condense the gas, how do you actually make this direct collapse extreme object in protogalaxies. So the idea earlier had been that if you start with a 3 sigma peak fluctuation at, say, redshift 15, and you follow the formation of the first star. So remember, in the first star game, you used to be able to make only 1 star. Then the simulations got better, and you actually saw that you could fragment and you could make many stars. So it turns out that now if you go to a higher significance peak, we find that you can possibly grow and you can make light seeds and yet grow them very, very rapidly. So another idea that we proposed last year to grow very, very tiny seeds very rapidly via super Eddington accretion in the early universe is in this context, where you have a gas-rich nuclear star cluster and you have a black hole that is essentially a test particle in the system, right? So the mass of the black hole is compared to the mass of an individual star, so it no longer defines the potential well. It random walks around, and because this gas is replenished by cold flows in the very early universe, you can actually grow it very, very rapidly to very, very high masses. So, and the idea of these direct collapse black holes is alternately that you have a packet of gas that makes it to the center. And again, this we are trying to follow up with simulations, and we can go so far as to see whether we can actually accumulate the gas at the center. So the new things that we've learned about direct collapse black holes recently is that the direct collapse actually occurs in halos that are satellite halos to halos where you form the first population of stars, because you need the Lyman-Werner radiation from this population to suppress molecular hydrogen cooling, to keep it an atomic cooling halo to permit the formation of a direct collapse black hole. So the new thing that we've learned is that the preferred sites actually end up being satellites to halos where you form stars. So the other new thing that we know about direct collapse black holes is that initially these black holes will be overmassive compared to the local M sigma relation at very high redshift. So these will be halos which have an overmassive black hole compared to the stellar population that is sitting inside it, right? So you form a direct collapse black hole, and either later you form stars in the same halo, or you merge with another halo that has either formed POP3 stars or POP2 stars, and you end up with a stellar component. So this tells you something about the journey onto the M sigma relation. And what it ratchets down to in terms of observables is at low redshift, at redshift 0, the implication, so these are 3 massive seeding models with varying efficiency, and this is the population 3 light seed model. And what you find is there's a difference predicted in the occupation fraction of black holes in low mass galaxies. And this is currently now testable, but the data from Amy Raines and collaborators is sort of just at the brink. And so we are really starting to push to have a better handle on what the occupation fraction. So here is my synopsis of where we are in this field. We think that you can start with massive black hole seeds, and as long as we suppress molecular hydrogen cooling with the Lyman-Werner radiation from nearby halos, you can somehow circumvent the last parsec problem. You can actually, with super Eddington growth, you can get the structure called a quasi-star or something. So these are the bits that are uncertain part of physics right now that we're working on. You can make a very massive seed, or you can start with a light seed, and you can super boost the growth in these incubators, which are, say, nuclear star clusters. But remember, the one element that we have to kind of sacrosanct assumption that we have to give up is super Eddington growth. As long as we permit super Eddington growth, even for a brief period of time, I think there's no problem. And I think there are now simulations, actually Ramesh Narayan, Jonathan McKinney, and others have shown that in simulations, super Eddington accretion is actually kind of a breeze, right? Yeah, it's really hard. Exactly. I mean, it's somehow we've had a theoretical hang-up about it. So, pardon? Oh, so you're rousing my loyalties now, right? So I think I'll stop here. And so so a lot of the results I showed you, sort of the snapshots, are coming from this project, the TCAN project, where we are looking at trying to understand the formation, fueling, and feedback from black holes. So there are many, many open questions, but we've made a lot of progress. And when I say we, I mean collectively, the field that's been working on the formation of the first black holes. Thank you. Yeah.
Another possibility is not so much how you make these equations. It looks like
stop growing.
So what is this fundamental limit that they run into? 1 after 10 billion solar masses and no more.
Yeah, so I mean, there are some basic physics arguments that we proposed earlier, but that's a great question. So somehow these behemoths by Redshift 6 have to tap out. They have to stop growing, or they have to grow very, very little, all the way from Redshift 6 down to Redshift 1 or even 0 locally. So I think the fundamental limit that one fundamental limit that we can think about is when the radiation pressure is high enough to really unbind any kind of fueling disk on very small scales. And so that's a fundamental limit. When the replenishment time for the gas, then if that becomes comparable to the Hubble time, then that's one argument that we can make for a fundamental limit. So, and the reason you can get away with making this limit is that all our current work is showing that the angular momentum of the gas at large radius is completely decoupled from the properties of the gas on very, very small scales that are relevant to the feeding of the black hole. So one can sort of get away and wave one's hands a lot and make an argument about the limit. But I think that's a really open question. Perhaps what happens in those cases is the stellar mass assembles and the black hole mass stagnates for these Redshift 6 quasars.
Right. So the silly title of this talk is Apology for a Silly Title of a Paper, which is really the work of my student Stephanie Keating. So this is kind of advertising for Stephanie's paper. And I'm frustrated, okay, that we had to use this silly title because I am not by nature an equivocal person. Okay, but somehow we had to equivocate on this, and it makes me mad, really. And so I want to justify why we had to equivocate on this thing. So the subject we were investigating, okay, is progenitor bias in these compact galaxies. Do I need to explain this phenomenon to you people? You know about this? Yes. Okay. So if you look at high redshifts, at a given mass, red galaxies tend to be significantly smaller than they are locally. Okay. So it's a factor of say 2 to 3 at redshifts of 2 to 3. All right. So somehow, quenched galaxies at high redshifts are more compact than they are locally. So one idea for this is that these galaxies are just getting bigger with time. Okay. So 10 to the 11th solar mass galaxy is 1 kiloparsec in effective radius at redshift 2, and by the time it gets to the local universe, it's suddenly 3 kiloparsecs through some physical magic that nobody understands. Okay, possibility A. Possibility B is that this is an observational selection effect that somehow we've screwed up. Okay, so the nature of this particular screw-up is that somehow these very compact, massive galaxies have existed at all redshifts. All right, so they and the idea is that at redshifts of 3, something forms. It's massive, and it's forming from a very gaseous environment, much more dissipative than if that same thing were forming locally. So at a given mass, okay, a thing forms at high redshifts, it winds up being more compact than if the same mass object were forming locally. Okay, so that's the idea of progenitor bias. So if this magic were to occur, okay, we would have to posit the existence nearby of a population of objects that are super compact, okay, 10 to the 11th solar masses, say, in 1 kiloparsecs inside. So, such things are not, up until recently, nobody has seen such things. Quite recently, and this is work done by Ivana Damjanov, who might even be here, there are now claims that such things are seen. But there's an easy way to test this idea, okay? And, what I'm positing is that there's a correlation at a given mass between the size of something and the age of something, right? So if I wanted to just test this idea, all I would need to do is find a population of very compact, massive objects and determine their ages of those stellar populations and test to see whether or not nearby more compact things tend to be older. It's a very simple idea, okay? So that's the effect we want to look for. So there's a problem, right? Because unlike, people like Priya and the first speaker who get to work with these simulations, I have to deal with the real world. All right, and so, or the real universe. And in the real universe, this is freaking difficult, okay? Because these are compact galaxies from the Deep 2 survey. So these are, hour-long spectral integrations with the Keck telescope. And this is the sort of signal to noise I've got to deal with, right? It's terrible. Right, so signal to noise levels of 2 to 3. And obviously, you're not going to look at this thing, measure a bunch of Lick indices, and get a reliable age. All right, so, you could just give up, or you could be desperate, okay? And, desperate people will do this thing that is called co-addition of spectra. All right, so I will take these poor quality spectra and I will stack up, 20, 50, or 100 of these things and attempt to generate a reasonable, respectable spectrum. So this is a product of a co-addition of between 30 and 50 of these very poor deep 2 spectra for these redshift 1 approximately galaxies. And suddenly these are respectable spectra. You can see the, prominent Balmer lines. And you could envision somebody clever like Charlie being able to come up with a mechanism for getting an age out of this thing. Okay, so why doesn't everybody do this? Well, the reason you might not want to do this is intrinsically it's dubious, right? I'm making all sorts of assumptions about whether or not the 30 or 50 or 100 things I'm co-adding are the same, right? So you can come up with all sorts of reasons why this is the last refuge of the damned, right? Nevertheless, you want to try and say something, and so this talk, okay, is sort of an investigation as to the wisdom of doing this, okay? And also to try to prescribe some limits on what you can infer if you're driven to do this thing. Okay, so let's pretend it all works, okay? Let's pretend this co-addition is spectacularly successful. Then you can, do the standard thing. You have these index model grids with these spectral parameters. And, Charlie has forgotten more about this than I'll ever know. You can plonk, collections of galaxies on this thing, and you can infer metallicities and ages, okay? So if I actually believe that I could co-add things, I could get ages out of them. But do I believe that I can reasonably do this co-addition thing? Okay, so let's look into what the biases are in this very typical example. Okay, this I happen to use deep, but you could use Cosmos, you could use any public data set out there, and you'd more or less be running up against the same problems that I'm describing here. Okay, so this is the co-added spectrum of a number of galaxies between, and I'll explain why, but between 20 and 50 red bulge-dominated compact galaxies. Okay, so this is the co-added spectrum. This is a slightly larger number of red bulge-dominated but not compact galaxies. Size is greater. In this case, we define compactness to be 2 kiloparsecs. Effective radius, and so this is and so the idea here is straightforward, right? You have two samples. One is the compact galaxies, and there's a control sample of non-compact galaxies. So relative measurement should be quite robust. Okay, so compact, non-compact. This is the number of galaxies that enter into this stack as a function of wavelength. Okay, so this is 3,500, and this is about 5,500 in the rest frame. So the point is, at any given position in this thing, there are a differing number of objects that went into making the spectrum. So that's the first evil thing, okay? So over here, I've got 20 or so objects that went into the stack. By the time I get to the longer wavelengths, I'm only stacking like 5 or so objects. Okay, so that's obviously bad. Okay, the other bad thing is, even though I, put reasonable limits on the available redshifts, I have to get enough galaxies to make this process worth doing, which means that I can't be too fussy. I can't take a very narrow redshift slice. It has to be significant. Otherwise, I wouldn't even have 50 galaxies to co-add, even in a ginormous survey like Deep. Okay, Deep 2. So that means that at any given wavelength, the mean redshift of the objects that went into this thing are going to be different. Okay, so here at 4,000 angstroms, then the mean redshift is about 1. By the time I get to about 5,500, mean redshift is more like 0.7. All right, so that's bad, because it means that if I'm looking for an age, this spectrum doesn't represent a consistent single age. Okay, it's a population of a bunch of different ages. So that's terrible. So what do? You give up? No. Okay, we have an approach to this, which is to embrace these problems. Okay, it's kind of like Microsoft, embrace and extend. The first speaker was talking about conformity. Priya was talking about obesity. So the next social ill I'm going to embrace is diversity. Okay, it's actually not an ill; it's a good thing. Okay, I'm going to argue that's a good thing. Okay, so what we've come up with is a statistical approach to this co-addition business whose emphasis is to try and characterize the diversity of the underlying galaxies that you stack. Okay, so the idea is to try and figure out whether or not the things that you are stacking are similar or not. So how are we going to do this? So we're going to I say use a bootstrap. It's really misuse a bootstrap. So do I need to explain what a bootstrap is? I don't mind doing it if I need to do it. I don't have a lot of time. If you don't know, you'll have to Google it. Okay, but the idea is basically sampling with replacement. So, and let me explain how this thing works with some simulations. Okay, so we have simulated here 100 ratty signal-to-noise 2 to 3 spectra. Okay, we're mimicking this deep experiment. And so if we make 100 simulated young galaxies, young in this context being galaxies that have a stellar population age of 2 gigayears, okay, we're assuming, very simple case here. Instantaneous star formation forms all of the stars at once, 2 gigayears old. And then you stack them and measure their ages, then this is the sort of thing you're going to get if you look at the distribution of ages, okay? So this represents the distribution of how many? 4,000 bootstraps on the same 100 simulated pore spectra. Okay, do the same thing, but with old galaxies. Now we have 100 old defined to be 7 gigayear-old spectra. Do the same thing. You get this. So you get nice Gaussians centered at the right ages. Okay, so if everything were perfect, this would work. Now the point is, what happens then if you start mixing things up? Okay, so instead of having just old or just young, you start mixing things up. In this case, if we take 20% of those spectra and make them old, make them 7 gigayears old, but 80% of them remain young, you get a distribution that looks like this. So its modality is fundamentally changing. So when it's roughly 50-50, you get a very wide, clearly non-Gaussian distribution with multiple modes. Okay, so that's the idea. So the idea is you misuse the bootstrap and you use the properties of the bootstrap to characterize whether or not your stellar populations going into your co-added spectrum are uniform or not. Okay, so I've actually only got one more slide. So if you apply this methodology to the Deep 2 sample of compact and non-compact galaxies, what do you get? All right, and specifically, do we see evidence for this progenitor bias? Well, this is where I have to equivocate. All right, if you define your sample using red bulge-dominated galaxies, you just use a color cut, you just use a Sircich model fit to the galaxy, the answer is no. All right, because if you look at the distribution of compact things versus non-compact things with this, bootstrappy approach, you see that there's a clear offset, and the implication here is that the compact galaxies are actually younger, not older, in this sample. However, if you're careful, okay, and rather than just doing this simple test, you also look at the galaxies first and you measure whether or not they've got deviations from good fits to these Sircich models, this parameter we're calling smoothness. In fact, you find maybe 1 sigma evidence, okay, for progenitor bias, or even just no effect at all. Okay, so this is a red, smooth, bulge-dominated sample. Okay, so the bottom line, okay, so the takeaways. Takeaway number 1 is you can come up with a statistical approach to co-adding spectra that attempts to answer the question of whether or not you're wise to co-add at all, and if you do, whether or not the initial population is diverse or not. And the second approach is if you want to look for these compact galaxies to try and assess progenitor bias, you have to worry about these fiddly little details about, how do you define an early type galaxy in these images with HST? Can I just measure one thing, or do I have to measure 3 or 4 things? And I think the answer is it actually depends what you do, and you get different answers. So hence the equivocation, and thank you. Oh, it's rough, huh?
The other thing to note is that there is also a size-age relation in humans, right? But it's exactly the opposite.
Yeah.
Because the universe was denser in the past, so galaxies were more compact. But for humans, the size of the world is
Indeed, it does. Sideways in some cases.
not uniform. Questions?
So why don't you do this with Sloan? Why don't you break your back with...
Yeah. Okay. So you have to cast back. You go back in time 2 years, where we thought that there was no evidence for local red nuggets, right? So doing it in Sloan, because people had looked for red nuggets in Sloan and claimed that there were not. So hence we were driven to redshifts of 0.5 to 1 in order to find some things in order to make the measurement. I think, with 20/20 hindsight, I would actually say if people like Ivana are correct, and I'm thinking yes, these things are in the local universe. They've been missed because, we've been misclassifying these galaxies as stars. And the right thing to do is, go back to Sloan with some more sensible star-galaxy separation thing, find these galaxies, and do exactly this thing with Sloan.
Thank you very much.
Okay.
Is that good? I can't talk loud anyhow, so gotta get it away. All right, thank you very much. Most of you know me. My name is Cameron McBride. I'm a postdoc here. So forget diversity. Let's use diverse properties to unify. So what I'm going to be talking about today is BOSS. It's a now done project, at least data-wise, that you may have heard something about. And what we're really focusing on is this baryon acoustics, spectroscopic survey in this project is to really look for the baryon acoustic oscillation in galaxy surveys. And just as a real brief review, I'm just going to touch on it for a second so we're all on the same page. The anisotropies in the CMB are analyzed. You look at the temperature power spectrum and you get kind of a distance scale of the first peak. This is very well calibrated in the CMB, and this is this pressure wave from early density perturbations. Right? But this density wave freezes out when basically this plasma goes away, and you have this kind of slight overdensity, and galaxies slightly preferentially form there, right? So that much later, once galaxies form and evolve, and the universe isn't quite so smooth anymore, you can actually measure the distance between pairs of galaxies and compare this ruler to this ruler, and learn about basically what the universe is doing between these two steps. And that gives us a large handle on what the universe is made of and whatnot. And how it does that is just simply the Friedmann equation. I'm not going to go into it. This is all the standard thing, but you have radiation, matter, curvature, dark energy, and the evolution of dark energy. So we do this basically in two different ways, just because of how the universe is set up. What I'm going to talk about is the isotropic, so just considering, it's isotropic in every direction, but you can do this along line of sight and across the sky, which we actually do in BOSS, to get a handle on the Hubble parameter directly, or this angular diameter distance. And so that's kind of the game of what we're doing. We're trying to measure the scale in the galaxy surveys. What we're doing with BOSS and is a very kind of simplified view. We take these nice, rich, beautiful galaxies, right? In our case, they look like cosmic cotton balls because they're mostly luminous red galaxies. And we just basically take an image, see them in the sky, then select the ones that we want, measure a distance, and basically make it a dot. So we make a three-dimensional map, and we convert these rich, interesting galaxies into dots that represent space. Then we analyze that statistically, this distribution. All right? We just do some very simple metrics on this distribution to figure out what the cosmic ruler is at this redshift loop. So this is large-scale structure. This is the game that we're playing. And so what we measure in the correlation function is a slight excess of probability that you're going to find a galaxy next to another galaxy, where you quantify that as a function of their separation. All right? And so this is the kind of galaxy correlation function as a function of radius for a low redshift sample and a higher redshift sample in BOSS from the DR11 results. We now have DR12 that we're analyzing. And what you see is it's kind of going down at larger distances there. It's kind of a power law at small scales. You'll see in a minute. But you have this peak bump. This is the baryon acoustic oscillation, the slight excess. It's hard to tell with these things, but it's only a really slight excess. But you can see it if you multiply by, say, the radius and scale it appropriately. So measuring where this is key to get these errors down and the more volume and stuff that we get on. But not all galaxies are the same. So let's just step back and treat everything like a dark matter halo. All right? If you measure the correlation function as a function of separation on smaller scales here, just because it's a power law, what you see is that more massive halos have a higher clustering. Okay, so not everything is equal. In fact, we think the same in galaxies. Brighter galaxies live in more massive halos, so they're going to be more clustered, right? They're going to be higher. And in terms of what we're doing of treating this point distribution, is we say the mass evolves. This is the handle on cosmology, right? We measure the galaxy correlation function by whatever selection we're doing, some convoluted combination of a whole bunch of different galaxy properties, right? And then we basically put a number that's a solid scalar, and we say that what we're measuring is essentially this B effective times the mass. It's a little bit more complicated, but that's more or less the assumption that we're doing. And so now we can just say, well, how is this B effective actually changing with galaxy properties, and can we take that into account? And that's basically the whole crux of the project that I'm describing here. Just to kind of point out, when we look at galaxies, what this is just the number density as a function of redshift, and you have different selections in the Sloan Digital Sky Survey. This is the main sample that's been analyzed in SDSS 1 and 2. This is the LRG sample that maybe made Daniel a little famous. And here we have BOSS, this lower redshift sample that I showed you, and this higher redshift sample. And you can see that, one, they're not flat, which is what you want. So the densities are a little bit different, right? And then you have these bumps and wiggles, and they kind of tail off. So over here, this is a magnitude limit. You see brighter galaxies at higher redshift. And over here, these are due to color selection so that we can choose galaxies from our image that are at the redshift that we want. So how do we treat these as the same? How do we just put a scalar in front of this and treat this as the same? What if we want to combine these? How do we deal with that? There's a little bit of work to do this in correlation function of just considering the sampling, right? The number density. One thing to point out is usually as you go to sparser samples, especially on this side, you're looking at brighter galaxies, so they're more clustered. So there's inverse relation between bias, right? But you can take care of the sampling because it contributes pair less in the correlation function. And this is the standard way to do it in this these so-called FKP weights. But all this takes into account is the number density, and it assumes the bias is changing, it is not changing over your sample. There was an update to this where you just consider this simple scalar, but it effectively changes with properties, and you integrate overall kind of those properties. I'm just using L for luminosity here to kind of do that, but it's a vector of any galaxy properties that you might care about. And so basically you're just updating this thing in an optimization way and creating a weight per galaxy that you throw in this, and all you're really doing is just making one little scalar a little bit more variable. Okay? That's really it. And then you integrate it and you do that. So this was worked out in theory here. It didn't make a big difference on the samples that they were looking at, but we're pushing 1% measurements in BOSS. So what are we doing? Just to highlight, it is actually surprising that the galaxies in BOSS are as uniform as they are, right? We tried to do that, but they're not. So this is showing I-band magnitude as a function of redshift. This is the lower low Z thing, so it goes to 0.5, and this is 0.3 to 0.8. There's a little bit of overlap. But what you're supposed to see is these are just density contours, is that these distributions do not look the same between the two, right? That's all you're supposed to see by eye. And that the distribution across these is not the same as a function of redshift. So if all of these represent different biases, how is this, the average of these, evolving over redshift? How is that the appropriate thing? It also varies over with color. Look at CMAS, you get a slightly bluer selection, that you get more of a scatter. Below this line is bluer, right? You get more bluer galaxies at higher redshift and less there, and so you have this distribution. So how do you account for that? So we just did the simplest thing, right? We said, well, they're going to vary some. In fact, it's not very redshift dependent. If you just look at the peaks, so this redder CMAS and the low Z sample, low Z is already a little bit red, kind of follow this curve. So as you get brighter, the bias, that's what this is, goes up. Right? I just fit a line to it, more or less. Right? And the blue galaxies, because you're getting more and more faint ones as you go higher redshift, are pretty much flat. So we'll just say, fine, let's just take this model, let's just apply it, what happens? Right? We basically see that the bias evolves as a function of redshift and goes up. Just the mechanics. Well, that's kind of what we expect, but if you consider this a constant number, what constant number do you do? Because these are volume averaged. Right? So we can account for that, and in fact, as you get a higher bias, you can pick out certain properties of your sample a little bit better, because features like the BAEO were more distinguished. And what this basically comes down to is the goal of the game is to get in cosmology is to get better errors. And the errors basically go as the effective volume, okay? When you're in this very high limit, you need larger surveys, okay? And so using a simple weighting, you gain maybe 5 or 10%, right, on the same sample. And you think, well, what's 5 or 10% when you're talking about this? We're getting a 1% density measurement, scale measurement, right? And this 5 or 10% is something like 500 square degrees to 1,000 square degrees, a free survey from implementing a very simple method, right? And that's basically what we're doing, is trying to do this and test this and kind of move forward and see, does this actually help? It helps actually a lot of some technical things as well, but it also gives us a way on the path forward. So EBOS is the next project, and there's a lot of heterogeneous different surveys. How do you paste them together? Can you really assume they're homogeneous or not? And this gives you a slight framework to start addressing these questions, or use them as tracers where you unify things that might be disparate right next to each other, but you can throw them together and use this type of analysis to actually do that. So you increase the effective volume, you normalize bias tracers galaxies to what you expect from theory mass predictions, all right? And then you can actually do things like cut the samples instead of Losey and CMAS. You can divide things up how you want to do for the science that you care about, okay? In our case, it's the BAO measurement, but you can do this with lots of things. And so you can do lots of this. And then, so most of this has been really testing how well this works, how well this theory works, whether or not we can produce this mock test, and how much of improvement this does. For example, density field reconstruction, if you might care about, and whatnot. And that's the goal of this project, which I hope to complete on very short order. And one of the reasons for that is actually I am saying goodbye to science, so I've just finalized a position in greener pastures in industry. And I just wanted to conclude on the last talk of the last ITC Luncheon this year. Thank you so much for everything here, and it's been really an honor to work with all of you at the Center for Astrophysics, and it's been a lot of fun. So, thank you. Thank you.
Any questions or comments? Well, if not, everyone have a wonderful summer and see you all in September.
Thank you.
What are you doing?
Oh,
When do you leave?
soon.
Soon, really?
Yeah. So how do you turn this off? There it is, off.